It's a simple question. Is math an invention or a discovery? You see a pile of three apples on a table. The idea of three, is that a real thing we just noticed? Or is it a concept, a word, a symbol we made up to describe what we see? Did we find the number three or did we invent it? This question goes deep. It's not just about numbers. It's about the very nature of reality, it's about what the universe is made of, and what our own minds are capable of. People have been arguing about this for thousands of years. There are two main camps, and they both have very good points. One side says math is a discovery. They believe that mathematical truths are out there, woven into the fabric of the universe. They exist completely separate from us. We don't create them any more than a sailor creates the islands he finds on a map. Pi, the ratio of a circle's circumference to its diameter, was true long before humans evolved to think about circles. The angles of a triangle added up to 180 degrees long before any Greek mathematician wrote it down. Our job is to explore this vast, invisible landscape of mathematical reality and report back what we find. The other side says math is an invention. They see it as a language, a powerful, precise language, but a human creation nonetheless. We invented the rules, the symbols, the axioms. It's a sophisticated game we play in our minds. It happens to be incredibly useful for describing the world, but that doesn't mean it's the world itself. We invented the concepts of numbers, lines, and sets, and from those inventions, a whole universe of logic blossomed. But it all started here, inside our heads. So, which is it? Are we explorers or are we architects? Let's look at the case for discovery first. It's a powerful one. The feeling that you're discovering something is very strong when you do math. You work on a problem, you struggle with it, and then suddenly you see the answer. It doesn't feel like you built it. It feels like you pulled back a curtain and saw what was always there. The solution was waiting for you. This is a common feeling among mathematicians. They don't talk about inventing a proof, they talk about finding it. The ancient Greek philosopher Plato had a big idea about this. He imagined a world of perfect forms. In our everyday world, we see crooked lines and wobbly circles. But in this other realm, this world of forms, there exists the perfect idea of a line, the perfect idea of a circle. Everything we see is just a shadow or an imperfect copy of these perfect mathematical objects. According to Plato, when we do mathematics, our minds are getting a glimpse into that perfect, unchanging world. We are remembering truths, not making them up. This might sound a bit mystical, but it captures a deep truth about math. The rules don't seem to be up for debate. 2 plus 2 equals 4. It's not a matter of opinion. You can't vote to make it 5. It's a fact. It's a fact on Earth, it would be a fact on Mars, and it would be a fact in a galaxy a billion light years away. This universality makes it feel like it's not ours. It belongs to the cosmos. Perhaps the most stunning argument for math as a discovery is something physicists have called the unreasonable effectiveness of mathematics. Why does this abstract thing, this system of symbols and logic that we play with in our heads, describe the physical universe so perfectly? It's spooky. When Einstein was developing his theory of general relativity, he needed a mathematical tool to describe curved space-time. It turned out that the tool he needed had already been created decades earlier by a mathematician named Bernhard Riemann. Riemann was just playing with ideas. He was exploring the logical possibility of geometries different from the one we learn in school. He had no idea his work would later be used to describe gravity. It was as if he had discovered a key without knowing what lock it would open. Einstein came along later and found the lock. This happens all the time. A mathematician will develop a new branch of math out of pure curiosity with no application in mind. Then, 50 or 100 years later, physicists or engineers will realize it's the exact language they need to describe something real. Things like knot theory, originally a purely abstract pursuit, are now used to understand DNA. Number theory, the study of prime numbers, was considered the most useless and pure form of math for centuries. Now it's the backbone of all internet security and cryptography. It feels like the universe has a hidden source code, and that source code is written in mathematics. When we do math, we're learning to read that code. We're not inventing the language, we're deciphering it. Think about something like the Mandelbrot set. It's a famous mathematical object, one of the most beautiful images in all of mathematics. To create it, you just take a very simple equation and feed its own output back into it over and over again. The equation is z does e2 plus c. That's it. A human invented that equation, but what comes out is not something any human could have designed. When you plot the results on a graph, you get this incredibly complex, organic-looking shape. And if you zoom in on the edges of that shape, you find smaller copies of the main shape, twisting and turning in infinite detail. You can zoom in forever, and you will never run out of new patterns. Swirls, tendrils, seahorse-like shapes. The complexity is infinite. No human being invented that complexity. We just wrote down a simple rule and let it run. The Mandelbrot set was waiting there, a consequence of that simple equation, we discovered it. It's like we found a mathematical continent that we never knew existed, we sail along its shores, awestruck by its endless coastline. Or think about prime numbers. A prime number is a number that can only be divided by itself and 1. Like 2, 3, 5, 7, 11, 13, and so on. We didn't invent the concept, we just gave a name to a property we noticed. Over 2,000 years ago, Euclid proved that there are infinitely many prime numbers. He didn't decide that this should be true, he discovered that it is true. It's a feature of the number system itself. The distribution of these primes is one of the biggest mysteries in mathematics. They seem to appear almost randomly, but not quite. There are deep patterns hidden in their sequence, patterns we are still trying to understand. Studying prime numbers feels like studying a natural phenomenon. It's like being a biologist studying the behavior of a strange species of animal or an astronomer mapping distant galaxies. You're observing something that has its own rules, its own existence, independent of you. So the case for discovery is strong. Math feels objective, it's universal, and it has this uncanny ability to describe the physical world. It really does feel like we're mapping a hidden reality, but that's not the whole story. Let's look at the other side. Let's look at the case for math as an invention. This argument starts from the foundations. All of mathematics is built on a set of starting assumptions. We call them axioms. These are statements that we agree to accept as true without proof. For example, one of the axioms of geometry is that for any 2 points, there is a straight line that connects them. But who says that's true? We do. We invented that rule. It seems obvious to us, but it's still an assumption. It's a starting point for our logical game. The inventionist argument is that all of math is just a consequence of the axioms we choose to start with. If we choose different axioms, we get a different math. It's like chess. We invented the rule that a bishop moves diagonally. There's nothing in the universe that makes that true. It's just a rule we made up for the game. Once we have the rules, we can discover all sorts of complex strategies and outcomes. But the game itself is our invention. The most powerful example of this is the story of non-Euclidean geometry. For over 2,000 years, the geometry laid out by the Greek mathematician Euclid was considered the truth. It was the only way to think about space. His 5 axioms were seen as self-evident. The 5th axiom, known as the parallel postulate, is a bit more complex, but it basically says that if you have a line and a point not on that line, there's exactly one line you can draw through that point that will never cross the first line. It seems obvious. So obvious that for centuries, mathematicians tried to prove it from the other 4 axioms. They couldn't. It bothered them. It felt like a loose thread. Then, in the 19th century, a few brave mathematicians decided to try something radical. They asked, what if the axiom is wrong? What if we just change the rule? A Russian mathematician named Lobachevsky created a new geometry where you could draw infinitely many parallel lines through that point. A German mathematician named Riemann created another geometry where you could draw 0 parallel lines. In his world, all lines eventually meet. At first, this was seen as just a weird game, a logical curiosity. They'd invented these strange, self-consistent mathematical worlds, but they weren't the real world. Euclid's world was the real one. And then came Albert Einstein. When Einstein was developing his theory of general relativity, he realized that massive objects like stars and planets actually curved the fabric of space and time. And the math he needed to describe this curved space wasn't Euclid's flat geometry. It was Riemann's geometry. The invented math, the one that seemed like a fantasy, turned out to be a better description of our universe than the one everyone had believed for 2 millennia. This is a huge blow to the discovery argument. If math is just out there waiting to be discovered, how can there be different contradictory types of math? And how can one of the fake ones turn out to be more real than the real one? It suggests a different picture. It suggests that we are the inventors. We create different mathematical toolkits. Then we look at the universe and see which toolkit fits best. We invented hammers, saws, and screwdrivers. The universe has screws in it, so the screwdriver is very effective. But that doesn't mean the universe is made of screwdrivers. It just means we built a tool that happens to work. We invented Euclidean geometry, and it's a great tool for building houses and measuring land. We invented non-Euclidean geometry, and it's a great tool for describing gravity and the cosmos. Think about other concepts we just made up. The number zero, for instance. For a long time, Western mathematics didn't have a concept for zero. It wasn't discovered in nature. There isn't a rock that is the number zero. It was an invention, a brilliant placeholder that made our number system work. It was a piece of technology we added to our mathematical language. Or what about imaginary numbers? The square root of -1. For a long time, mathematicians called them imaginary because they seemed impossible, a logical absurdity. You can't have a number that, when multiplied by itself, gives you a negative, but they were a useful fiction. They helped solve certain equations. So mathematicians kept using them, holding their noses while they did. Then, it turned out these imaginary numbers were the perfect way to describe things in the real world, like alternating current in electrical engineering and the wave functions of quantum mechanics. This feels like invention. We create a new piece for our logical game because it's useful or interesting. Then, we're surprised to find that this new piece helps us understand the world in a new way. It strengthens the idea of math as a language. We can invent new words and new grammar, and sometimes these new linguistic tools allow us to express ideas about reality we couldn't express before. If math is a universal truth we discover, you might also expect every culture to discover it in the same way. But that's not what happened. Different civilizations developed different number systems, different notations, and different ways of thinking about proof. The rigorous axiom-based proof that we associate with math is largely a Greek invention. Other cultures had sophisticated mathematics, but their approach was different. This suggests that math has a cultural, human element. It evolves. It changes. Universal, unchanging truths probably shouldn't do that. So the inventionist argument is also very strong. Math is built on axioms we choose. We can change those axioms and create new maths, and we invent new concepts like zero and imaginary numbers to solve problems. It looks a lot like a system we build, not a world we find. So where does that leave us? Stuck between two compelling stories, one where we are humble explorers of a cosmic truth. The other, where we are the proud creators of a magnificent mental palace. Maybe the problem is the question itself. Maybe forcing a choice between invention and discovery is a false dichotomy. Maybe the truth is somewhere in the middle or is a combination of both. Let's try to build a bridge between the two ideas. One way to think about it is this. We invent the concepts, but we discover their consequences. Think back to the game of chess. Humans absolutely invented chess. We made up the board, the pieces, and the rules. The rule that a knight moves in an L shape is a pure human invention. There is no platonic knight-ness out there in the universe. But once we have invented the rules, a whole world of consequences opens up that we have to discover. We have to discover the best opening moves. We have to discover that a king and a rook can beat a lone king. We discover complex strategies that unfold over dozens of moves. No single person knows all the consequences of the rules of chess. The supercomputers are still exploring the vast space of possible games, discovering new things. So, chess is an invention, but playing chess at a high level is a process of discovery. Maybe math is like that. We invent the basic rules, the axioms. We invent the concept of a number, or a set, or a point. These are the pieces in the board. But once we've set up the game, the consequences are fixed and objective. They are out of our hands. We have to discover what happens next. We invent the definition of a prime number. But the fact that there are infinitely many of them is a discovery. We invent the formula for the Mandelbrot set. But the infinite beautiful complexity it contains is a discovery. We invent the axioms of geometry. But all the theorems you can prove from them are discoveries. This feels like a more satisfying answer. It gives credit to human creativity, but also acknowledges that feeling of objective truth that mathematicians experience. We are architects, but the building materials we use, logic itself, have their own rigid properties that we cannot change. We decide to build an arch, but the laws of physics determine whether it will stand or fall. There's another way to see it, which focuses on our biology. Perhaps math is not a feature of the universe, but a feature of our brains. Our brains evolved to survive in this world. To do that, they had to get very good at recognizing patterns. Finding the pattern of a predator in the grass, understanding the quantity of fruit on a tree, perceiving the geometry of a landscape to navigate it. Our brains are pattern matching machines. Maybe mathematics is simply what happens when we take this innate biological ability and refine it, formalize it, and turn it into a language. The basic intuitions about quantity, space, and pattern are our biological discoveries about how to process the world. The formal systems of mathematics we build on top of them are our inventions. This would explain why math is so effective at describing the universe. It's not that the universe is mathematical, it's that our brains process the universe in a mathematical way, and we've created a formal language to express that processing. We're not reading the universe's source code, we're describing how our own brain's software works. This leads to a beautiful analogy: math as a lens. We don't see reality directly. We see it through the lens of our minds. Mathematics is the process of grinding that lens, making it more and more precise. We invent a new mathematical concept, which is like grinding a new curve onto the lens. Then we look through it and discover that we can see the world more clearly than before. Newtonian physics was a powerful lens. It let us see the orbits of the planets, but when we looked at things that were very small or moving very fast, the image was blurry. So, we invented new maths, quantum mechanics, and relativity, which were like new, more powerful lenses. They brought those blurry parts of the universe into sharp focus. The universe is what it is. The lenses are our inventions. The clear images they provide are our discoveries. This view respects both sides of the argument. It doesn't force us to choose. So what's the final answer? There isn't one, and maybe that's the most important point. This is a question that likely has no definitive solution. Its value is not in the answer, but in the asking. Thinking about it forces us to confront the deepest questions about who we are and what our relationship to the cosmos is. Are we just clever animals who invented a useful game of symbols, or are we something more, beings capable of perceiving a timeless, universal truth? But the truth is, it feels like both. When you're lost in a mathematical problem, you feel a sense of creative freedom, of building something new. You are inventing. But when you find a solution, a proof that is elegant and simple and true, it feels like you've touched something eternal. Something that was true long before you were born and will be true long after you're gone. It feels like a discovery. In the end, it doesn't diminish mathematics to see it as an invention. What an incredible invention it is. A language that allows us to build bridges, send probes to Mars, and understand the beginning of time. And it doesn't diminish humanity to see math as a discovery. How amazing that our minds, which evolved on this small planet, have the capacity to connect with such profound and universal truths. Whether we are composers or archaeologists of the spirit, the result is the same: a stunningly beautiful and powerful understanding of the world. The debate over whether math is an invention or a discovery is a reflection of its dual nature. It is both a product of the human mind and a window into the universe. It is the most powerful tool we have ever created, and the most mysterious thing we have ever found. And the line between creating and finding is perhaps not as clear as we think.